here we take a look at like 3 types of systems. This first one, energy can go in and out and matter could go in and out. Okay, so this would be like when you burn fuel in your car, the gas energy leaves that system of your car, but also so does the fuel. It's burned and the vapors go away. So that would be considered an open system where both matter and energy can leave. A closed system would be one where matter stays in there, but the total energy can change. So maybe this would be like if you had ice cubes sitting in a glass with a lid on it, the heat or the thermal energy in that case of the ice cubes, if it's in a room, the heat from the room, I'm drawing with blue so it's kind of confusing, could go into that, but the matter itself, the actual ice cubes and the water, they're all going to stay the same. Okay, so energy goes in and out. For our class, for the sake of just getting started with conservation of energy, we are going to work with what is called isolated systems. These are clearly idealized situations where neither matter or energy leave the system. Okay, and how we define that system, matter or energy leave the system, is kind of up to us. But if we think back to like a marble on a ramp, we would define this as our system. And so we're saying that within that system, no energy is going to be created or destroyed. Now, just like conservation of matter in chemistry, it can change form. So it can go from being GPE at the beginning of a ramp to KE at the bottom of the ramp. So it can change forms, but the total amount of energy would remain the same. So looking at an example of a system here, we have this girl and she's at this little energy skate park and she's going up and down. But right now, the system is not isolated. And our main hint that it's not isolated is right here. We can see that thermal energy is getting bigger and bigger and bigger. And so over time, she's losing some of that heat or that energy as heat, which leaves the system into the surroundings. And so that would have been an example of a non-isolated system. For, like I said before, for the sake of ease to kind of get us started out right now, we will start with isolated systems. So I'm going to try to turn off friction here. And so now what I want you to realize, because this will help us, it's very kind of basic, but it helps us along the road here, is as she goes up in height, you'll notice that potential energy comes up to its maximum, and then they kind of swap between potential and kinetic energy. And so if I pause that, oops, I gotta switch clickers here. If we pause that kind of midway through, like right now, if we were to look at these 2 bars at this height, so she's not at the very bottom, but at this height, her potential plus her kinetic energy is going to give her the total energy of that system. And then I'm going to play it one more time and just watch how this bar goes up as that one goes down. Well, the total energy stays constant. That is our conservation of energy. That was my phone, sorry. Okay, so we'll watch this play out here. And so noticing total energy staying constant, just kind of transitioning between kinetic and potential energy.